All right, this is section 11.8. This is video 2. In video 1, we talked about the radius of convergence, and now we're going to go ahead and talk about the interval of convergence. The good news is, by doing what we did in video 1, we've pretty much done everything we needed to do for video 2 as far as finding the interval is concerned, with one small exception. So we've kind of figured out what the interval was. The only difference is we have to test the endpoints of those intervals. So if you remember, there was 3 ways that you could be convergent. You could be convergent only at the center, you could be convergent everywhere, or you could also be convergent within a couple of bounds. And typically what happened there was you would get that inequality that you would have to say, okay, the absolute value of this thing was less than 1. We'd split it up, and it would be in between -1 and 1. When you get one of those, you actually have to test the 2 endpoints of your compound inequality that you get to see whether it's actually convergent or divergent at that particular endpoint, because everything in between will be convergent. It's just going to be whether it's going to be convergent at the endpoints that we have to check. And that's where all the prior series testing stuff that we did in the beginning of this chapter is going to come into play, because we're going to have to utilize those things to be able to figure out what's happening at the endpoints. All right, let's jump into a couple of examples, and hopefully this will just make sense as we go. But if not, we can always, you can go back and watch it again, slow it down, whatever you need to. But really, you're going to be using all the prior series testing stuff that we've done. Okay, first example. We want to find the interval now of convergence of the sum of x to the n power. So the first thing we do is we do exactly what we did before. We're going to take the limit as n goes to infinity of absolute value of x to the n plus 1 over the absolute, over x to the n. So the n plus 1 term over the nth term. Of course, that's just going to reduce to the absolute value of x. The limit of the absolute value of x as n goes to infinity, again, there's no n, it's just going to give you the absolute value of x. And we want that to be less than 1. So that means that we want that inequality to be between -1 for x and +1. So the radius of convergence here is 1. It's not asking for, wait, is it asking for? No, it's not asking. Yeah, it does say to first find the radius of convergence, which we have just done. Our radius of convergence, our rock, is 1 because it was centered at 0, and it's 1 unit from either end of the center. What we need to check to see is this actually convergent at -1, and is it convergent at +1? Well, how you do that, and you have to remember, these are x values right here. We are going to take those values, those endpoints, and we're going to say, okay, when x is -1, what does my power series look like? Well, that means you're going to literally plug in -1 in for your x and see what you get. So you're going to have the series -1 to the n power as n goes from 0 to infinity. So as n goes to infinity, what is happening to -1 to the n power? So go back through your tests that we've talked about. Can we just use the nth term test here? That's probably the one you want to try right off the bat. If not, it's an alternating series. Can you try the alternating series test? If not, can you do a geometric? Can you do something else? You're going to have to try and pick out which series makes the most sense here. Well, this one right here is literally -1 to the n. So as n gets bigger and bigger, it's going to bounce back and forth between -1 and +1, which means it will never approach anything finite. The limit as n goes to infinity doesn't exist. The limit of -1 to the n as n goes to infinity does not exist. Therefore, because we just applied the nth term test and we got something other than 0, it's divergent at -1. So now let's check what happens at +1. X equals +1. So now the series from 0 to infinity, Again, plugging a positive 1 in for x in the original series just gives you 1 to the n power, which is really just 1. But again, your limit test is the easiest one to do, the nth term test. The limit as n goes to infinity of 1 to the n, it's just going to keep getting bigger and bigger. It's going to go to infinity. So this one is also divergent. And because both of the endpoints were divergent, our interval of convergence, or our IOC, not ROC anymore, is going to be -1 to 1. And these are both parentheses. If it included one of the endpoints, it would be a bracket. All right, let's move on to the second one. Again, hopefully that makes sense. And hopefully now you can see why we had to learn all those different series tests, because we're going to use those to check all of our endpoints for these intervals of convergence. The nice ones are going to be if you get 0 or if you get infinity, because then you have nothing to check. Okay, find the interval of convergence of x to the n power over n. So we'll do the limit as n goes to infinity, absolute value, x to the n plus 1 over n plus 1, times the reciprocal, which is n, over x to the n. So the limit as n goes to infinity, reducing, is going to give me x on top, and then n over n plus 1. So we'll just make that like over 1, make it easier there. The limit of the n part is going to go to 1, which really just leaves us with the absolute value of x, which once again we need to be less than 1 in order for it to be convergent, which just means that x has to be in between -1 and 1. So very similar to the last one. We just have a different series to plug these things into. So again, our endpoints, let's check the endpoints. When x is -1. The series now becomes the series n equals 1 to infinity of -1 to the n power over n. And hopefully what you can recognize, that is the alternating harmonic. So basically that is an alternating series. So by the alternating series test, it's the alternating harmonic. That series is convergent at -1. Now let's check what it does at +1. So now the series from n equals 1 to infinity is just 1 to the n, which is just 1 over n. Okay, and hopefully you recognize that one as being the harmonic, which is a p series, or p is 1. You can state it either way. I'm just going to state that it's harmonic, which basically says that it's a p series, p equals 1, which is divergent. So that means that our interval is going to go from -1 to 1, where the -1 is convergent. So our IOC, the -1 is convergent, but the +1 is divergent. It'll look like an I. So there is your interval of convergence. It did not ask for the radius in this. Obviously, the radius would be 1 in this case. But there's your interval of convergence, where you actually have part of it which is convergent, part of it which is divergent. Both endpoints could be convergent. As we've already seen, both endpoints could be divergent. And it doesn't matter which endpoint it is. It could be one or the other if you've got a split. But you got to check the endpoints. All right. Moving right along. And again, once you've gotten to a certain point, you may or may not need to keep doing all the problems. It's up to you as to how many of these things you need to watch. All right, limit. So we are looking for interval of convergence again. So limit as n goes to infinity. I'm going to drop the -1 for right now. It doesn't mean anything as far as finding the radius part. X plus 1 to the n plus 1 over 2 to the n plus 1 times the reciprocal, 2 to the n over x plus 1 to the n. So simplifying, let's see, we are going to get, that is going to leave us with an x plus 1 on top, and it looks like it's going to leave us with a 2 in the denominator. And that has to be less than 1, which means that negative 1 is less than, nope, not less than or equal to, is less than x plus 1 over 2, which is less than 1. Solving that, multiply everything by 2, we get negative 2 is less than x plus 1 is less than 2. Subtract 1 on either side, you're going to get negative 3 is less than x is less than 1. So our interval of convergence goes from negative 3 to 1. Everything in between those numbers is going to be convergent. We just have to check the endpoints. So let's check x equals negative 3. Now, we could drop the negative 1 when we did the limit test for the absolute convergence, but when we go to plug these things back in, we need to keep that negative 1. It's part of it. It's part of the original series. So we're going to get a series from 0 to infinity of negative 1 to the n. Plugging a negative 3 in to this x right here is going to give me a negative 2 to the n over 2 to the n. So simplifying, you do have to kind of remember some of your properties here. On the numerator, I've got a negative 1 to the n times a negative 2 to the n. Because they're both being raised to the same power, you can multiply what's inside. So ultimately what that gives me is a series. The numerator just becomes a positive 2 to the n, and the denominator becomes a positive 2 to the n. So that's just the series of 1, which means I'm adding up an infinite number of 1s, which means that that is divergent. So let's check the other endpoint when x is 1. So if I go from n equals 0 to infinity, we'll have negative 1 to the n. Plugging a 1 in for x gives me a 2 to the n over a 2 to the n. Well, the 2 to the n's are going to cancel themselves out, which means I've got an interval, a series from n equals n0 to infinity of just negative 1 to the n. We've already shown that by the nth term test, that one is divergent, which it is. So neither one of these endpoints converges, which means that our interval of convergence goes from negative 3 to 1, not including either endpoint. All right, I'm going to try and keep motoring so that this video isn't too awfully long. Okay, we actually kind of did this one up in the top, but I will go ahead and at least redo the interval part. N goes to infinity. That was negative x over 4 to the n plus 1 over negative x over 4 to the n. Okay, so reducing that is going to give us the absolute value of negative x over 4. Absolute value will get rid of the negative sign, so that means my limit is the absolute value of x over 4, which once again we want to be less than 1. So that just means that negative 1 is less than x over 4, which is less than positive 1. Multiplying both sides, all three parts by 4, excuse me, should give us negative 4 is less than x is less than 4. So we have to check those endpoints of negative 4 and positive 4. So if x equals negative 4, plugging in negative 4 into x right there, it's going to give you a negative 4, technically over negative 4, which is just 1. So you're going to get the series n equals 1 to infinity of 1, or 1 to the n. Either way, you're adding up an infinite number of big numbers, which is going to go off to infinity, so it is divergent. At x equals 4, now you're going to get negative 4 over positive 4, so that's just going to give you a negative 1 to the n. And again, we've done that one several times. Nth term test tells you divergent. So our interval is going to go from negative 4 to 4, IOC, negative 4 to 4, not including either endpoint. All right, number 5. Limit as n goes to infinity, absolute value, x plus 4 to the n plus 1 over, so n plus 1 will be n plus 2, n plus 1 plus 5 will be n plus 6, times the reciprocal, n plus 1, n plus 5, over x plus 4 to the n. So it looks like the only thing that's going to reduce here is the x plus 4 parts. Limit as n goes to infinity, absolute value. That should leave us with an x plus 4 on top. And then we're going to have n plus 1, n plus 5 over n plus 2, n plus 6. So it looks like the dominant thing of n's in the numerator and the denominator is going to end up being an n squared, so their coefficients are just 1. It looks to be like our limit here is the absolute value of x plus 4, which once again we want to be less than 1, which means that x plus 4 is in between negative 1 and 1. Subtracting 4 on both sides, we are all three parts, keep saying sides. It's going to be negative 5 is less than x is less than negative 3. So your radius of convergence would be 1. Again, it's not asking for that. Interval is going to go from negative 5 to 3. We just need to figure out whether the negative 5 and 3 are included. So let's do that when x is negative 5. So if I plug in negative 5, the sum is going to become, let's see, plugging it in there, it's going to be a negative 1 to the n over n plus 1, n plus 4. And it's going to go from 0 to infinity. So that one pretty clearly looks like it's an alternating series. I've got a negative 1 to the n over top of something. And it looks like if you were to apply the alternating series test, the limit of the absolute value of that would approach 0. And the terms, the absolute value of all the terms would decrease because literally the numerator would not change, but the denominator would get bigger. So again, this is what I meant when I said those are going to be relatively obvious in these circumstances. So you can say by the alternating series test, that one is convergent. And again, you don't really need to show an awful lot when it comes to that because that's pretty obvious overall. If it's something which is not obvious, we'll have to use another method. So if we plug in negative 3 now, all that makes that numerator is a positive 1 to the n, which is just positive 1 over n plus 1, n plus 4. All right, unfortunately, the limit test for as n goes to infinity fails because that just gives us 0. This is not an alternating series. It's pretty clearly some kind of a polynomial in the denominator. To me, the limit comparison test would be the easiest way to go here. Certainly would not want to try to do the integral test or on something like this. Direct comparison test, you probably could find a direct comparison on this one if you really wanted to. The limit comparison seems to be the easiest. If you were to multiply everything out in the denominator, you would get a 1 over n squared as your dominant term. So you would compare this, limit comparison, b sub n would be 1 over n squared. So since 1 over n squared is going to be, here, I'll write this out over here, b sub n would be 1 over n squared. And that's a p series, so it's convergent because p is 2, which is greater than 1. So p equals 2, greater than 1, therefore convergent. And if you use the limit comparison test, so by the limit comparison test, if you multiply by the reciprocal of 1 over n squared, you're going to get the same power on the top and the bottom, meaning the limit would give you a finite number, so they are both convergent. So this is also convergent, which means both endpoints are going to be included in your interval. So the IOC here is negative 5 to negative 3 inclusive. of both endpoints. I think it's the first time we've had one of those where it's actually included both endpoints. But again, hopefully you can see how, like I said, the tests, I hope, are relatively obvious as to what's going to happen with them. It doesn't take an awful lot of work to figure them out. Again, I hope that's the case. Maybe not. All right, find the interval of convergence. Just looking at this one, by the fact that there's a factorial in the denominator, and technically the numerator, when you plug an x value in, is going to be some kind of an exponential. I'm thinking this is going to be convergent for everything. Again, hypothesizing that, but let's check it out to see. So we'll take the limit as n goes to infinity of absolute value x minus 1 to the n plus 1 over n plus 1 factorial times n factorial over x minus 1 to the n. Let's see reciprocal. So this reduces, let's see, the limit as n goes to infinity of the absolute value should be x minus 1 on top. N factorial over n plus 1 factorial will leave n plus 1 in the denominator. Since n is the only thing approaching infinity, the denominator grows while the numerator doesn't do anything, so this one will approach 0. 0 is always less than 1, which means this should be convergent everywhere. So our interval of convergence is from negative infinity to positive infinity. And again, that's because 0 is always less than 1. So it doesn't make any difference what value of x you plug in here. This will converge everywhere. All right, a few more to go. This is n factorial times x plus 3 to the n. I'm willing to bet this is going to be divergent for everywhere except the center, but again, we'll check it out to see. There's no fraction here that you're dividing by anything, so it seems to me like this will just get bigger and bigger and bigger no matter what, unless it's right at the center. So it'll be absolute value, n plus 1 factorial x plus 3, that is an x plus 3, let's write that again, x plus 3 to the n plus 1 over n factorial x plus 3 to the n. So the limit as n goes to infinity, simplifying the factorials, it looks like we'll end up with an n plus 1 on top. Simplifying the polynomial part, x plus 3, it'll just be x plus 3 on top. So we're going to get n plus 1 x plus 3. And since n is going to grow infinitely, we're going to get infinity here, which means the only way this is convergent is at the center. So convergent only at, in this case, x equals negative 3, which would have been your center, your c value. So there really is no interval of convergence, it's just at the center. All right, two more. So we've got a limit as n goes to infinity. Okay, we're going to drop that negative 1. It doesn't mean anything for the absolute value part. So we'll have x minus 2 to the n plus 1 over n plus 1 times the reciprocal n over x minus 2 to the n. So the x minus 2 part is going to give us just an x minus 2 in the numerator. Looks like I'll still have an n left over, and we'll still have an n plus 1 because those won't reduce. The limit of the n parts goes to 1, which leaves us with the absolute value of x minus 2, which again we want to be less than 1. So we'll set x minus 2 in between negative 1 and 1 and solve for x. Adding 2 to everything should give us 1 is less than x is less than 3. So our interval of convergence goes from 1 to 3. We now need to check the endpoints. So when x equals 1, our sum from n equals 1 to infinity will be negative 1 to the n. Plug 1 into x here, which is also a negative 1 to the n, over n. But negative 1 to the n times negative 1 to the n becomes a positive 1 to the n. So really what you get is the sum of 1 over n, which again you should recognize as the harmonic. That is harmonic, which means divergent. Let's check x equals 3, which should now give us the sum from 1 to infinity. Negative 1 to the n times 1 to the n, which is just 1, over n. Well, the second one, the positive one up there, doesn't really mean anything. So ultimately you have negative 1 to the n over n, which again is the alternating harmonic or alternating series test, and that gives you convergent. So our interval of convergence for this one should be from 1 to 3, not including 1, but including 3. That is your interval of convergence. All right, one more. We should be able to keep this thing under 30 minutes, which is good. Again, I'm looking at n squared times x plus 1 to the n. More than likely, this is divergent, except for at its center, because I've got nothing to divide by. But let's just double check to make sure. Limit as n goes to infinity, absolute value of n plus 1 squared, x plus 1 to the n plus 1, divided by the original term, which is n squared, x plus 1 to the n. So that will reduce. The n plus 1 squared and the n squared don't simplify, but the x plus 1 to the n plus 1 gives you x plus 1. So taking the limit of the n stuff is going to give you 1, so we get absolute value of x plus 1. So I was actually wrong in this case. I think it is going to have an interval of convergence, because that has to be less than 1, which means that x plus 1 has to be in between negative 1 and 1. So we'll subtract 1, and we get from negative 2 is less than x is less than 0. So we have to check out negative 2 and 0 and see what we get. When x equals negative 2, the sum from n equals 2 to infinity is going to be n squared. Negative 2, plugging that in here, is going to give you a negative 1 to the n term. So it is an alternating series, but the limit does not approach 0, so we can't really use that. As n gets bigger and bigger and bigger, this thing is going to approach larger and larger and larger negative and positive values, so it will go off to infinity in both directions, so it simply does not exist, which means we don't include the negative 2. If x is 0, we get the sum of n squared. Plugging in a 0, you get 1 to the n, but that's just 1. So it's a sum of n squared as n goes from 2 to infinity. That goes way off to infinity, so that also does not exist. Which means that our final interval of convergence for this section goes from negative 2 to 0, not including either endpoint. All right, again, you did not necessarily have to watch all these examples. If you did, thank you for sticking with me for the entire time. But that's all there is to it. You're just trying to find the intervals and radius of convergence. That should be plenty enough, and we will build upon this stuff in the next section.